We are here from Allen High School teaching advanced chemistry, both AP and IB, focusing on atomic theory and structure. We were discussing getting into the solutions to Schrodinger's equation and quantum numbers. Right now we're focusing on the principal quantum number n. And that is our energy level that you remember gives us information about energy as well as distance from the nucleus. As you increase the energy, you increase the distance from the nucleus. So there's a formula developed by a guy named Rydberg and called Rydberg's equation. Now there's a constant named after him as well, but fortunately the people at AP, the lovely people, have combined Rydberg's constant and Planck's constant and I think the speed of light to give us this value here. So that's the constant. It's, just accept it. It's a series of other constants. That's Z. That's the nuclear charge. For now, we're going to discuss the nuclear charge as if it's equal to the number of protons in the nucleus. Now, that's not quite true, we'll see, but it's a good estimate as a starting point, and certainly to get into the concept of spectroscopy and how we learned about some of the different structure and function issues of an atom. Now, let's take a look at the diagram that would be based upon this. This is called an energy level diagram. And we're moving into what is typically called atomic emission spectroscopy. A single spectrum is UM for singular, spectra is plural, and I'll be showing you some of these in class. But I want to get some terminology down before we do that. I'll actually show you some lamps and we'll use some fun goggles. You may have remembered them from 10th grade, but it's okay, they're still pretty psychedelic. And then also you'll be looking at a video on that and you'll see it in a little more detail. Now, before we do that, let me explain what this diagram is. This diagram is an energy level diagram. It is an increase in potential energy in that direction. So energy is increasing there. You can envision the nucleus as being way down below this, further down than this. This is certainly not to any scale. Now, we need to get a few terms down before we talk about what these arrows are and what this diagram is. First off, the concept of ground state. We want to get that back in your memory. Ground state. In the ground state, all electrons are at a point where attractive forces to the nucleus have been maximized and repulsive forces between one another have been minimized. And we're going to find out how to predict that ground state soon. We're going to develop models and really revisit models on that. A good portion of this is review from pre-AP, much needed, but still review from pre-AP. So that's called the ground state. I'm fond of saying that my ground state, my lowest energy state is, sitting at home in the rocker, likely with the cat in my lap. I'm a little old lady with the cat in her lap reading the comics. It's kind of my most relaxed state. Now, electrons can be elevated to what is called an excited state. An excited state. Now, to go from a ground state to excited state, so let's say the electron was here in its ground state and went to an excited state, whether it was 2 or the 3 or 2 to 3, can move, depends on the number of electrons, how many movements there are. It's an absorption of energy. And so you notice that for going from the ground to the excited state, my final N is greater than my initial N. And that's going to be a positive energy change. It's going to require energy, that change in energy. So we would have to provide some energy. Now, that energy coming in to cause excitation can be done through electricity or, fire, current, light. There's a lot of ways we can do that. Now, my excited state, this is the analogy I like to use, is that if I'm sitting in my ground state and my phone rings and it's Denzel Washington, I'm going to be excited. I'm going to get energy from that. And you notice I'm moving further away from the nucleus. I'm going to get up off my rocking chair and I'm going to be pacing around. And you can bet I am very, very excited. So those are some key terms there. We've got ground state. You want to make sure you write that down. Excited state, that the final is greater than the initial, that it's going to be a positive change in energy, which we would call absorption. So make sure you write all that down that I'm about to erase. Now, let's talk about what happens after something has been excited. So now, an electron is up a higher level. Now, electrons want to maximize attraction to our nucleus. I'll put that a Z down there for nuclear charge. They want to maximize that attraction. And so electrons don't stay excited for very long. And those electrons are going to go back to at least some empty hole that gets them closer and closer to the nucleus. And that process is called relaxation. So in my analogy, Denzel Washington realizes very quickly that he has the wrong number, sadly. And, after I talk to him for as long as he's willing, we hang up. And eventually, I'm going to sit back down. I'm going to relax again. But, I've got all this pent-up energy, and I need to do something with that pent-up energy. And so I'll probably pace around. I'll likely call my sisters. I'll call my husband because he knows all about my obsession with Denzel Washington. But eventually, come on, the novelty's going to wear off. I've got to come down to earth, where we live and breathe and have our being, and I'm going to relax. I'm going to sit back down. I'm going to finish the comics. Now, notice here for relaxation process that the final is less than the initial. And we'll do some math on this and you'll see. So our change in energy is going to be a negative value. So we need to, as we look at that negative value there, that would be called an emission process. So the other was called absorption. This is called emission. And you should understand all those terms and predict whether a transition is an emission or an absorption, whether or not a transition represents relaxation or excitation, and whether the change in energy would be negative. Now, earlier, I mentioned that my energy was, mechanical, physical, kinetic kind of motion, the kind of the kinesiology type thing, and heat. In this case, the energy has to leave. We can't create or destroy energy. That's kind of this minor law that we tend to try to obey in science. And that energy in this case is going to be released or emitted. And it's going to be emitted in the form of electromagnetic radiation. So the energy coming in can be of a variety of types, but the energy being released is electromagnetic radiation. And so we're going to be back to dealing with the energy of the photon involved. So the energy of a photon. Now, if we have energy of the photon, we can ultimately get to wavelength of the photon. And this would show an emission spectrum, like what we would see. The lines that end at n equal 1 have the biggest energy. So you notice this has a very large energy drop here. As I increase that delta energy, I'm going to have a shorter wavelength. So that series, called the Lyman series, is going to be in the ultraviolet range. The Balmer series, which is what you're going to be able to see with the spectroscopes in class, ends at n equals 2, and that's in the visible range. The visible range goes from about 700 nanometers to 400 nanometers. And in between is Roy G. Biv. Now, the Paschen series ends at n equals 3, and that's in the infrared region, below the red. So that gives you an indication of some of the transitions and some of the terminology. Now, we don't see anything in between here. Why do we see sharp bands? Well, it's because it's quantized. The electron can't just drop halfway. Remember, it can only have set, discrete energy values. So the electron either drops to here or drops all the way to here. There's nothing in between. Therefore, there won't be any wavelengths in between. Now, I have a video assigned for you that goes to an animation that will elaborate on this a little bit. And you need to watch that, and you need to take notes, because that's part of what I'm going to be looking for when I walk around and get your notes grade. So in the next video, we will start doing a few calculations with this. I know some of you really are comfortable with your calculator, and we're going to be getting that. So for now, signing off.